Okay. So, this lecture will discuss about that analog to digital conversion. So, I am not talking about that circuit for analog to digital conversion. I am talking about the information which is required for digital signal processing purpose, that analog to digital conversion. So, let us start. If I see a DSP system, digital signal processing system, DSP system, what is a DSP system? People may ask. So, if you see, there is a signal which is analog. So, x t is an analog signal. Let us say it is a sin 2 pi f t. Let us say f is the frequency, t is the time. So, this is analog signal. Now, you apply the analog signal to a analog to digital converter. So, ADC, analog to digital converter. So, to do that analog to digital conversion, there is a anti-aliasing filter, sampling and hold. I will come. So, my purpose is I have an analog signal which is varying in analog. I have to convert to digital signal. What is digital signal? Digital signal is nothing but a sequence of a number. So, 2, 5, so those are called sample. So, which is nothing but a x of n. Sometime it is written x of n is written like this way. So, instead of first bracket you can use third bracket to represent digital signal x of n. Okay. So, x of n which is a sin 2 pi, but n t, if you see continuous t, this 2 pi f and f will be there, f n t, continuous t is divided by n t. So, t is the fixed distance, so I will come. So, a digital signal is nothing but a series. So, how I convert the analog signal to digital signal? And once I get the digital signal, suppose I told you multiply x of amplify x of n 3 dB. 3 dB means double. So, I can double that signal sample value. So, 2 into 2, 5 into 2, like that way I can do. So, it is nothing but an algorithm. So, which is nothing but a digital signal processing. Okay. And then there will be, so I have any DSP system, input is analog signal has to be converted to a digital signal. So, how do I convert an analog signal to a digital signal and what are the limitations? That is the discussion for analog to digital conversion. So, how do I convert? Let us say you do not know anything about analog to digital conversion. So, what we have? We have an x t which is nothing but a, let us say, sin 2 pi f t, continuous t. So, I have a signal like this, let us say. Now, what I want? I want a sequence of sample. So, there is two things I have to do. One is that you know that discrete time signal. I have to discretize the time axis first. So, digital signal is a discrete time, discrete valued. So, I have to first digitize this time axis, discretize this time axis, and then I have to discretize this amplitude axis also. So, when I discretize the time axis, that is called sampling. Now, when I discretize this amplitude axis, this is called quantization. You know that discrete valued signal is nothing but a quantized signal, and discrete time signal is nothing but a time axis is discretized. So, how do I discretize the time axis? Let us think of simple things. I have a circuit like this, and here I am applying the signal. I am collecting the signal on these 2 points. So, if I operate this switch on and off, so when the switch is on, I get the signal. When the switch is off, I should not get the signal. So, if I say I apply a sine wave in the input, so in output I will get like this. Let us say initially switch is on. So, at 0 0 value I get a value. Then I let us say after t time switch is again, so initially switch is on then off. So, after t time switch is on again, then I get a value. After another t time switch is on again, I get another value. So, it is t, it is 2t, like that way I can get. So, I am collecting the evidence of the signal at a 0, t, 2t, 3t. So, distance between these two sample is t. So, what I am doing? I am taking a sample of the signal. So, when you say that if you see in a mandi or when a farmer comes with a lot of rice, trucks of rice. So, it is impossible to check all the rice packet. So, what you do? We take a sample, some sample. So, sample means I am selecting on a continuous space, I am selecting certain time. So, that is sampling. So, how do I do sampling? So, along the time axis, I take the evidence of the signal at certain interval. So, that interval is nothing but, so that interval actually I am operating the switch. So, if I say I am operating the switch with a time interval t, then what is the frequency of operation of the switch? Is nothing but a 1 by t. If the time interval is t, so on and off. So, initially on, then off, then again on at after t time. So, on to on is nothing but a period. So, that on to on is t time. So, I know the frequency of the operation of the switch is 1 by t, which is nothing but let us say Fs, which is called sampling frequency. So, if I want to sample an analog signal which is continuous in time, I have to discretize the time axis, I have to multiply or I have to do some operation by which I can take the evidence of the signal after certain time interval. So, if I ask you, if I want to do it mathematically, so what I have to do? So, I have to operate this switch. What do you mean by operating that switch? That means I am multiplying xt with the impulse whose time interval is t. When the impulse is come, switch is on. When the impulse is got, switch is off. And the distance between the two impulse is t. So, that is called sampling frequency or sampling signal, and the frequency of this impulse is called sampling frequency. Okay, I know that. So, now I say suppose I have a signal, let us say sine wave signal. Now, if I take the evidence of the signal, let us say here, here and here, can I get back the signal again? Because after the digitization, after the processing of the signal, I have to again convert it to the analog signal. So, the main purpose of the signaling is that I have to reconstruct that analog signal again, which is called analog to digital conversion, AD. So, digital to analog conversion, DAC. So, I have to revert back the signal again. So, I operate the switch such a way in a sine wave, I take the evidence in here, here and here, all are 0. Can I get back the signal? No. So, there is a problem. How frequently I should operate the switch such that at the output, from the output signal, I can revert back the input signal. You know that instead of taking this entire signal, if I take let us say this point, this point, this point, this point, this point, this point, I can make an interpolation and I can get back the continuous signal. So, the limitation is after what interval I should switch on or switch off, or I can say what should be the sampling frequency such that at the output from the discrete signal, if I apply digital to analog conversion, I will revert back the analog signal. That is called sampling theorem. So, Shannon sampling theorem. Sampling theorem. So, if the highest frequency content in the analog signal, so input signal is oscillating, let us say FM, highest frequency component, okay, of F max is equal to B. B is the bandwidth of the input signal, and the signal is sampled at the rate of Fs is greater than equal to twice F max or twice B, then xt can be exactly recover of its sample value using the interpolation function. So, what sampling theory is limited that what should be the frequency operation of the switch, at what rate I should operate the switch, so that from the discrete time instant I can get the continuous instant again back. So, that is the limitation of selecting my Fs. So, what will happen if Fs is not greater than equal to twice B, then what will happen? And what will happen if the Fs is equal to twice B and the signal is pure tone? So, what will happen? As in, how can I explain that things? So, let us say I taken slides here. So, what I said that if my Fs is not greater than Fs is not greater than equal to twice B, the B is the bandwidth of the input signal, what will happen? Forget about the frequency domain representation, that part I am coming later on. First you think about what is a frequency of a signal. So, suppose I draw a sine wave like this and I draw a sine wave like this. Which one has a high frequency? This one. So, frequency means more oscillation. So, if I have a signal look like this, so that means this signal contain more frequency. Frequency components are high because lot of small oscillations are there. Now, say this is my signal and let us say I can say this is my complete oscillated signal and I want to sample that signal like this way. So, what I miss? I miss the point. Which point I miss? I miss the point this one, this one, this variation, this variation. So, if my Fs is not greater than 2B, I am missing those small variation in the signal. So, when I reconstructed the signal will be not that variation, signal will be smooth out. So, that means I am losing information. But what is the requirement of the sampling theory? I want to get back the original signal. So, that is the time domain representation. Now, I come to the frequency domain. So, what is the frequency domain? If I say, if I have a sine xt is equal to, let us say, sine omega t, let us say sine omega t plus theta is my signal, then what is the frequency domain representation? So, if this axis is omega, I know it has a peak in here and it has a peak in here, which is positive omega, which is called minus omega, that is 0. So, that is the frequency domain representation of a sine wave. Now, suppose I have a baseband signal whose bandwidth is B. So, this is my baseband signal up to B bandwidth. So, signal has a frequency, input signal has a frequency component from 0 to B hertz, that is my bandwidth. Now, if I multiply that signal with a impulse whose frequency response is Fs, whose frequency is Fs, what should I get? You know, suppose I told you I have a sine A. If I multiply a sine B, what should I get? 2 into half, 2 into sine B, A into B. So, I can convert it to the cos A plus B minus cos A minus B, like that way. So, I get a two component, one component is A plus B, another component will be A minus B. So, if the A is high, so I can say under the A there will be a B, A plus B and A minus B. So, this is A, then it is A plus B and this will be A minus B. So, if I multiply this, I have a baseband signal like this. When I multiply with Fs, so this is my Fs. So, I will get this one and I will get this one. This is Fs plus B, this is Fs minus B. At the beginning also at the 0 also I get, this is 0, B minus B. Then I get twice Fs, this. Now see, if Fs is less than twice B, that means I just drawing the positive side. This side there is a B, let us say these kind of things I will get. So, here Fs is less than twice B. My baseband signal bandwidth is B and Fs is less than twice B. So, what will happen? There will be some overlap. In this case, Fs is greater than twice B, then I can get a separation. Okay. So, if there is a overlap, then when I process it, when I convert to digital to analog conversion, so those information will be missing, overlap. So, that is called aliasing effect. And in time domain representation, what I said, that I have a signal which has a small variation. If I sampled it in a which is not greater than B twice B, then I will miss this small variation. Then also this is called also aliasing. And if I explain it in frequency domain, this is exactly this. So, what is the requirement? If I have an analog signal, I have to guarantee that Fs is not less than twice B. It should be actually greater than twice B, or at least it is equal. Even if it is a periodic signal, monotonous signal like the sine wave, even Fs is equal to twice B, then also I cannot extract the signal. So, if I have a sine wave signal, let us say frequency is F0, then what is T0? Is 1 by F0. Let us I have a sampling frequency Fs. Fs should be equal to twice F0. So, I can say Ts is equal to T0 by 2, because you know T0 is 1 by F0. So, Ts is 1 by Fs. So, if I convert, then I can get Ts is equal to T0 by 2. So, the difference of the sample, so this is 0th position, I take T0 by 2 here and next one will be here. So, this is 0, this is 0, this is 0. I cannot get back the sine wave again. So, if it is a pure tone, I cannot say the Fs will be twice B. Fs must be greater than twice b. So, in that case I require a one sample here, one sample here, one sample here, one, then also I can get back the signal. So, that is the limitation of sampling. So, sampling frequency, what is sampling? Sampling is nothing but a discretize the signal time axis. So, if I go for the mathematical representation, so I have a sampling means x of n is equal to, actually if it is, let us say x of t is equal to cos omega t, this is continuous frequency, x of n will be cos omega n, or I can say it is nothing but a cos this omega into n into t. Forget about this part will come later on. So, it is nothing but I am discretize the time axis. So, n is the index. So, it is 0 index, it is t, it is twice t, it is 3t, like that. So, n is the index and t is the interval between the sample. So, in mathematics, if I have an analog signal which is cos omega t, in digital domain it will be cos omega n into t. Okay or not? So, now take another slide. So, I say x of x a t is equal to cos omega t. Now, I said x of n is equal to cos omega into n into t. So, let us say this omega is called analog frequency or analog frequency. What do you mean by analog frequency? It is nothing but a radian per second or hertz. Hertz is radian per second, here. Now, here second is not there because I have digitized the time axis. So, this omega, what is this omega? It is nothing but a cos omega into n divided by Fs, because t is nothing but a 1 by Fs. So, now it is come cos omega by Fs into n. It is written as cos omega n. This omega is called digital frequency, or this is radian per sample, and this is radian per second. So, once I digitize the signal, the sampling frequency is divided, it is radian per sample. So, this omega is nothing but a radian per sample. If I say this omega is equal to twice pi f, f is the frequency, okay, hertz, f the frequency in hertz. So, if it is like this, then I can say this will be cos 2 pi f divided by Fs into n. So, there is a f by Fs term will be there. Okay. So, radian per sample, radian per second. Okay. Sometimes this is called discrete frequency. Okay. So, I will come what should be the highest rate of oscillation, that part I will come later on. So, now as per this analog to digital conversion from sampling theory, what limitation it put? It put the limitation the Fs must be greater than equal to twice b, unless I cannot correctly reconstruct the input signal, analog signal again. Because if you see, all real life signals are analog signals. Suppose I said I have a DSP processor, or I want to store that my voice digitally, what is there in your internet channel, or when you downloaded this MPEG 4, my digital audio is there. So, how do I get the digital audio? So, my voice is recorded by a microphone, produce an electrical signal which is analog, which is continuous in time. then it is converted to digital signal using an ADC, analog to digital conversion. So, when it is start converting from analog to digital, it is multiplied by an FS sampling. So, sampling theorem has to be held there, and if you see, once I recorded it, then once I want to play it again, what I require? I have to again convert from the digital signal to the analog signal and apply to the loudspeaker, then only you can listen it. So, if FS is not satisfy that criteria, then digital signal cannot be again converted to the analog signal. So, on my voice you cannot get from the loudspeaker. So, that is the sampling theory. So, when I want to design an ADC, so I have to restrict it that the bandwidth of the signal, if it is B, or I can say if the sampling frequency of the ADC is Fs, then bandwidth of Xt must be restricted to Fs by 2. So, bandwidth of the ADC is Fs. If I select sampling frequency is 4 kilohertz, then I have to restrict the input signal bandwidth to 2 kilohertz. So, how do I restrict it? It is called filter. What filter? It is nothing but a low pass filter whose cutoff frequency is Fs by 2. So, I have to restrict the input signal to Fs by 2 by a filter. So, which is what kind of filter? It is a low pass filter. High frequency should not be there. So, that filter is called anti-aliasing filter. What it is done? It restricted that Fs must be greater than or equal to 2B. So, that aliasing part in frequency domain, when I explaining that this part should not be, there will be no aliasing, no overlapping section in here. Is it clear? So, that is why this anti-aliasing filter is there. Then there is a sample and hold. So, after this anti-aliasing filter, if I multiply with a sampling frequency impulse, so what I get? I get a discrete time instant. So, each are called sampled. Each are called sample. Each sample then required to be quantized. So, how do I quantize the sample? That required at some time. I have to quantize that sample. The value of the sample must be converted to a binary number, because computer only understand binary. So, how do I convert it to the binary number? There are a lot of process to convert it to the binary number that require a time. So, for that time I have to hold the signal. So, I require a sampling and hold for that purpose. Then I quantize the sample, I get a binary value, binary representation of the sample. So, in a digital signal, every sample is nothing but a number, index number, sample 1, sample 2, sample 3, sample 4, sample 5. So, I have explained how do I convert, how do I discretize the time axis. Now, in the next lecture, I will explain how do I discretize the amplitude axis, that is called quantization. So, how do I quantize a signal? Okay. So, that is called quantization. So, you can say, have you heard about 8-bit ADC, 16-bit ADC, 24-bit ADC, 32-bit ADC? What is that 8-bit ADC? What is 24-bit ADC? That is linked with the quantization. Okay? Thank you.